In the second part of lesson 2, what we're going to do is we're going to learn some theorems to help us prove that quadrilaterals are parallelograms. Some of these will actually be the converse of the theorems that we learned last time. You remember last time's theorems started off with, if a quadrilateral is a parallelogram, then both sets of opposite sides are congruent. Okay, these theorems are going to start with, if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So that would be the converse, and that's the first one we have here. That's definitely the converse of one that we learned last time. If both pairs of opposite sides are congruent, then we know the quad is a parallelogram. If both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral's a parallelogram. That is also a converse from one of the theorems we learned last time. Third one, if an angle of a quadrilateral is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. That's almost a converse, but the wording is a little different, so not exactly a converse. And the next one says, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. That's definitely a converse from one we learned the other day. And of course, you're making flashcards for all these so you can remember them. And finally, if one pair of opposite sides of a quadrilateral is both parallel and congruent, then the quadrilateral is a parallelogram. We didn't have a theorem like this last time, but this is a good one. It kind of gives us a shortcut if we're trying to prove that we have a parallelogram. So if I have just one set of opposite sides and I know they're both congruent and parallel, then I know that that quadrilateral is a parallelogram. So we've got to do some examples here, and we're going to start with a proof. Prove that if an angle of a quadrilateral is supplementary to both of its consecutive angles, then the quadrilateral is a parallelogram. So we're proving the theorem that we just learned on the other page, which of course means we can't use that theorem in our proof. All right, 1, write down the given. Angle J is supplementary to angles K and M. That's given. Oh my goodness, you know what I got to do? I got to come over here and draw myself a picture. I can't believe they gave me this with no picture. So what have I got? J, K, L, M. All right. So what is that given piece of information? J is supplementary, J is supplementary to K. So if I call this X, I'm just going to call this one 180 minus X, because that's what it is. M would also be 180 minus X. Yes, if they're supplementary, I mean, that's the best way I can think of to mark it. Okay, so let's see, what does that tell me? Oh, I know. This tells me that KL is parallel to JM. So KL is parallel to JM, because look, if this is a transversal and these two angles K and J are supplementary, then I know that those two are parallel. And what do I also know? I know that KJ is parallel to LM, right? Let me double check that. KJ is parallel to LM. Because if I look at here's KJ, and here's LM, and if I use this as my transversal, then those two angles are supplementary, they're consecutive interior angles. So yeah, so those are true statements. I've got two sets of parallel lines, and how is it that I know that's true, that those two sets of lines are parallel? Because the consecutive interior angles are supplementary, so that's going to be the consecutive interior angles converse, right? It's the converse of the theorem that tells me my lines are parallel, all right? And so that gives it to me, right? That gives it to me. I now know that JKLM is a parallelogram. And what is it? How is it I know that it's a parallelogram? Oh, because that's the definition of parallelogram. A quadrilateral with two sets, both sets of its opposite sides parallel. So definition of a parallelogram. That's how I know that's a parallelogram. Okay, so there's our proof. All right, everybody okay with that? If you're not, put a star on it. We'll talk about it in class. Okay, and now I think what we have left are just a few more sample problems. Yeah, I'm probably going to let you, I'll do this one and I'm going to let you do the last page by yourself. A pane in a stained glass window has the shape shown below. Is it a parallelogram or is it not? That's what we'd have to decide. Well, look, I got 21, 21, 45, 45. So of course, yes, it is. And the reason I know is because that theorem that says both pairs of opposite sides are congruent. And I'm just going to put in parentheses, that's a theorem, because everything's a theorem except for, you know, the definition that says both pairs of opposite sides are parallel. So I don't want to get confused about the theorems and the definitions. I mean, the definition of parallelogram. Okay, so I'm going to let you take on these. Oh, actually, there are quite a few, and there's another proof. So let me take a look here and see which ones I want to do and which ones I want you to do. Okay, I'm going to work this page with you, and I'm going to let you do the last page on your own. Can you prove that the quadrilaterals below are parallelograms based on the given information? Well, let's see. What do I have? I got 5 and 5. Okay, I would need to know both sets of opposite sides are congruent. And let's see. I got 50. Oh, look. This tells me these are parallel. They're parallel by the consecutive interior angles converse. So yes, indeed, ABCD is a parallelogram by the theorem because one pair of opposite sides is both parallel and congruent. Remember, that's one of our theorems we learned today. Okay, how about this one? HK is congruent to HI. JI is congruent to JK. Those are not opposite sides, so no, not enough info. Not enough info to know whether that's a parallelogram or not. Can't prove it. Can't prove it's a parallelogram. Okay, and how about this one? EF is congruent to GD, and DE is parallel, but they're not the same set of sides. I would have to know that one set of sides is both congruent and parallel, so there's not enough info here either. Not enough info here to prove that they're parallel. And finally, I'm going to try to beat the bell. ALN congruent to DNL. This one's congruent to this one. What does that tell me? It tells me that's parallel to that. It tells me that's parallel to that. And that is enough information. I do know that LAND is a parallelogram by the definition of parallelogram. So I want you to work the back page, even try the proof, come back and check, and I'll have the solutions up for you. Okay, so here we are back to check the problems that I left you to work on your own. And they're just asking me, what do the values of the variables have to be so that ABCD is a parallelogram? So I look at the first one. I got two ways to go. I know opposite angles have to be congruent, or consecutive angles have to be supplementary. So that's the theorem that I used right here, and I found out that x is 15. And then I did the same one where the measure of angle A plus the measure of angle B has to be 180, and then I solved that for y and got 25. Okay, down here, what do I know about opposite sides of a parallelogram? So since opposite sides have to be congruent, 2y plus 2. Oh, I took the 2. I took AB and CD because they both just have the variable y. I set them equal to each other, solved for y and got 11. And then I just used sides AD and BC, set up my equation, and got x equals 3. Please put yourself a note here if you need to ask about these in class. And finally, on this last one, what do we know about these angles here? Well, if this is a parallelogram, we know they're congruent, right? Because these are alternate interior angles. This, and if this is a parallelogram, all the pairs of opposite sides have to be parallel. So that means that has to be parallel to that. And if that's the case, then those two angles are congruent. So when I set them equal to each other, solve for x, I get 24. And then I decided not to fill in this proof because it is pretty basic, about as easy as you're going to get. So I want you all to do that proof, and then we'll check it tomorrow in class.